Hello there, this is Dr. Dell again, or Craig Hane, and I'm going to talk to you on this video about what is called integral calculus. Now, there's two types of calculus that I mentioned in the introduction. There's differential calculus and integral calculus, and you should have already watched the video on differential calculus because this video would not make complete sense unless you had done so. So if you haven't done that, please go back and watch that video. Here's what integral calculus is all about. Once again, we're dealing with functions. And so let's start with a function here. We'll call it f of x. This is the x-axis. This is the y-axis. And we have a function here. I'll just rotate it like that. And the question now is, what would be the area underneath this function if you went from a to b? That's the question. And it turns out that we have a notation for this area. We actually call it the integral from a to b. We put in the upper and the lower limits. And this is the function y equals f of x. So we write f of x dx. And this is this area. And this is the definition of what is called the integral of f of x from a to b. Just that simple. Now, it turns out that this is a concept that's extremely useful in science and engineering. What you're wanting to do is accumulate things here. And in fact, this notation is kind of intended to be suggestive of just what's going on. Here's what we could think of here. Let's say we take a point right here and we call it x. And let's say we take and look at what does that mean then? If we go up here, this is the height. What's that height right there? If this is x, what's this height? Well, of course, it's f of x. That's what this notation means. So this height is f of x. Now let's say we went out a very small distance here. We'll call this small distance d of x, or just dx rather. And so this then becomes x plus dx. And then we go up and we look at this rectangle. And what would be the area of this little rectangle? Well, its height is f of x, and its width is dx. So if you multiply them, this would be the area of that little sliver of a rectangle. Now, if dx is really, really small, that's a very narrow rectangle. And so if you want to know this total area, and let's say you divided this into 1,000 subintervals, so that dx was 1/1000th of the interval from a to b, then you'd have 1,000 of these little rectangles, and what you're really doing is you're adding them up. This is the Greek letter for summation, summa. So this is intended to indicate then that you've taken all of these little rectangles and you've added them up from starting at A and going to B. Now, if you were using actual dividing this into intervals and actually calculating the areas of little rectangles, you'd see there's a little bit of error up here for every one because at the top here, this isn't a complete straight line. And so this would not be an exact area. However, if you divide this into enough subdivisions, this summation of these rectangles will be as close to the real area as you want it to be. And in calculus, this is assumed to be an infinite subdivision. dx is assumed to be what's called infinitesimal, meaning that it is it's not zero, but it's very close to zero. And so that's the definition of area. Now, the problem then is, how do you calculate? The areas or the integrals, the definite integrals. That's really the problem. How are we going to calculate these integrals for these areas? And this was a problem our ancestors faced. They found out that they had many applications in science and engineering where they had this type of a problem. For example, you could start out and say, okay, what is going to be the area underneath this parabola? This is y equals x squared. And if we're going to go out here to say A, what is going to be this area? And Archimedes solved this problem. It's called the quadrature of the parabola, and he actually came up with an answer for it. But it isn't obvious what it is. As a matter of fact, it turns out that this area is a cubed over 3. But how would you know that? How would you guess that? Similar problems, actually a circle. What is the area of a circle? And again, Archimedes solved this problem. If this is a radius r, then he found out that the area of the semicircle is 1/2 of pi r squared. And he was able to find that out. Archimedes, this applies not only to areas, it applies to volumes. If you want to know the volume of something, then you would divide it into disks. For example, if you took a sphere and if you divided it into little slabs, little circular slabs, and added them all up, you would be able to calculate the volume of the sphere. And Archimedes did do that. As a matter of fact, it was a tour de force for an ancient mathematician to do that. But these are the kind of problems then that integral calculus is designed to solve. And this comes up in many, many, many applications in science and engineering. So that is the problem that our ancestors were faced with. Now, it turns out a remarkable thing happens to be true. And that's what I want to tell you about next. As you may recall from the last video in differential calculus, what we did there is we had a function f of x, and we derived its derivative function, f prime of x, where every point here was the slope of the point up above. And you go back and watch that video if you've forgotten it. And then we calculated a bunch of derivatives. We found out, for example, that if you had the sine function sin x, then its derivative was the cosine function, cosx, and things like that. But I told you at the time at the end of that video that a very, very difficult problem in general is to start with a function down here and work backwards and find out where did it come from. This is the so-called antiderivative problem. So we've got an antiderivative problem. If I give you an arbitrary function down here and say, where did it come from? What function would it have been the derivative of? In other words, what is this antiderivative? That's a very hard problem. Now, you might not think it's hard because if you happen that you can find it in your table of derivatives, then you've got the answer right away. But this in general is you don't know what it is. For example, if I said, what is the antiderivative of the cosine of x? Well, you're lucky enough if you've done your table, you can say, well, I know that the sine of x has its derivative as cosine, so the antiderivative is sine. And I might also point out, and I didn't mention this in the first video, that if you have two different antiderivatives of a given function, they only differ by a constant. So you could take the sine of x and add any constant to it, and that would also be an antiderivative. But if you had another function that was the antiderivative of the cosine of x, you could be sure it was the same as the sine of x plus a constant. So that's the problem. Now, it turns out that there's a remarkable, remarkable solution to this problem that was discovered by a group of mathematicians in the Middle Ages, in the 1600s as a matter of fact, and here it is. Suppose you take, and we're going to now, to keep the notation straight, we're going to call this the t-axis. I just want to use a different variable. And so this will be a function y equals f of t, okay? And I'm going to graph it here. And so this is the y-axis. And we're going to start over here at A. And now we're going to come over here and we're going to call this the point x. This is the point x now. This is the t-axis. So this would be f of a here, and this would be f of x up here. This would be the point. Come over here, you get f of a, and if you come over here, you're going to get f of x. And this doesn't matter. This works for any curve we're going to talk about now. Now, let's define a new function, capital F of x, to be the area under the curve, under this curve, from a to x. So now we're going to say f of t dt, and we're going to take the area from a up to x, okay? Now think about this a little bit and rewind the tape if you need to. As always, when I'm doing these tapes, if you've got a question you're not sure, you should rewind it and watch it before you go on. All I'm saying here is, let's take a function, and if we call this the t-axis, it'll be a function called y equals f of t. And let's start at the point A and let's go over to the point X. And now we're defining a new function f of x, just to be the integral or the area from A to X of under f of t. And if x changes, of course, then that capital F of x changes. This x now itself is a sort of a meta variable, if you want to call it that. Now here is the remarkable fact. This f of x, if you take its derivative, just turns out to be this original function, little f, evaluated at x. That's the remarkable facts. And this, in fact, is called the fundamental theorem. If we need say so, of calculus. Now, when you first see this, it almost may leave you cold. You may say, what is he really saying here? Well, what I'm doing is now, what we're doing, what our ancestors have done for us, is we are relating now the concept of integral, which is continuous summation, its area. We're relating that to the concept of rate of change. The rate of change of this accumulation of area is equal to whatever it is we're accumulating the area under, the f of x. Another way to write this is that f of x is the antiderivative of f of x. Remember, if you had a function and took its derivative, then its antiderivative was just the function again. So this is another way to write this. This is the derivative way of writing it. This is the antiderivative way. In other words, if you went up to your table that we had earlier, you remember we had a table. You've got up here, you've got, for example, you've got the sine of x, and down here you've got the cosine of x. What are we doing here is we've got up here, we've got f of x. Down here we've got the derivative of f of x. The other way is antiderivative. What I'm saying is if you start with an unknown function here, f of x, you can get its antiderivative by just simply taking the integral from f of t dt from any point, it really doesn't matter where you start, a, up to x, and that's the antiderivative. And this was the key that our ancestors discovered that unlocked really made modern science possible. Because if you're going to do modern science, you're going to have to calculate integrals. And we didn't have computers back in those days, as you very well remember. They didn't have calculators. Doing arithmetic back in hundreds of years ago was extremely difficult. So they had to have a way of evaluating these integrals without trying to calculate 1,000 little rectangles and add them all up. And this was the key to that. And so that's what I wanted to tell you about, really, particularly in this video, is that this was the key to our modern science and technology. Okay, now let's see how we might apply the fundamental theorem of calculus to solve problems of area. Certainly this is the way our ancestors did it. And so let's take a look at that. Now, let me remind you or recall for you that if you have a function f of x and you take its derivative, f prime of x, then the antiderivative is going the other way, and you could take this f of x and add a constant to it, and you would still get the same f prime of x because the derivative of a constant is 0. After all, a constant represents a horizontal straight line, and it has a 0 slope everywhere. But it also turns out, and it's easy to demonstrate, that if you have any antiderivative, it will be f of x plus c. It'll be equal to that for some constant c. So now let's suppose, and looking at this the other way, let's say you take an arbitrary function g here, then we've learned that one of its antiderivatives would be the integral a to x of g of t dt. And suppose you knew another antiderivative already. You had, I'll call it capital G of x. Then you would know that these differed by, at most, a constant. And so if you already knew an antiderivative, now you would be in a position to evaluate this integral. Because the integral from a to b of g of t dt, and by the way, t is a dummy symbol, I can say g of x dx, it doesn't matter, would be this antiderivative evaluated at at b, and then of course plus some constant. And the question is, what is the constant? And that's very easy to see by going back up here. If you let x over here be a, then you get 0 on this side. If you go from a to a, g of t dt, this will clearly be 0 since you didn't go anywhere, and that will be g of a plus a constant. So g of a, or rather the constant, is just negative g of a. So we come back up to here. This is g of b minus g of a. So now what that boils down to then, we can say that if you have an antiderivative of little g, and I'm going to use x as a dummy variable now, and you have an antiderivative, you can evaluate this integral by just taking g of b minus g of a. And this is another way the fundamental theorem of calculus is always often presented, because it's the way you actually use it then to evaluate integrals. And so it's equivalent, of course, and follows from everything I'd already said. But now let's see this in action and how this is the tool that really enabled our ancestors to use calculus then to solve practical problems in science and engineering that involved integrals. So let's go back now and take a look at some examples of that. Let's start out with one of the examples I mentioned earlier. Let's just take the parabola y equals x squared, and let's ask ourselves, what is the area under that up to the point A? Now, in order to, what we're really asking then is what is the integral from 0 up to the point A of the function x squared dx? That's the question we're asking ourselves. How can we evaluate that? Now, one way to do it is to divide it into many, many, many little rectangles and add them all up, but that's a tremendous amount of effort, particularly if you don't have modern computers and tools to use and you're just doing pencil and paper. It'd be very, very hard to get an answer to that way. So we go to our table of antiderivatives and we look and see what we can find, or our table of derivatives, and we start searching through it. And we find up here that if we have x cubed divided by 3, its derivative is x squared. We would find that in our tables. Well, that means then that we can evaluate this integral by just taking the antiderivative x cubed over 3 and plugging in a, and subtracting, plug in the first limit, which is 0. And of course, 0 cubed is 0, so the answer then is a cubed over 3, which I mentioned to you earlier in a previous video. But now this is a proof of that utilizing calculus. Now, Archimedes didn't have calculus, so he had to go about it in a much more difficult way, and that's why it was a great achievement, and the other Greeks weren't able to do so. Now, let me just give you a few more examples, so hopefully you will begin to really appreciate the power of this. Let's say that I wanted you to tell me what is the area under the cosine function for 1/4 of its cycle. So we're going to start at 0, and we're going to use radian measure, go up to pi over 2, and I want to know this area. And this is the cosine function. Well, we go to our table of derivatives. I'll move up here to do that, and we say, gee, could we find something where this ended up down here being cosine x? And of course, earlier we did that. I told you that if you take the sine of x, take its derivative, you get the cosine of x. So we've already seen that. So the antiderivative of cosine of x dx is sine x. Always you can add a constant if you want to, but you don't need to because the constant will fall out when you do the definite integral. So now we know that the definite integral from 0 to pi over 2 of the cosine of x dx, that'll be this area, is simply going to be the sine evaluated at pi over 2 minus the sine evaluated at 0. And if I had sine x plus c here, don't you see you'd have had c minus c canceling out. So I didn't need to put the plus c in as far as doing this calculation, because it would have just canceled out. Well, now the sine of pi over 2 we know is, let's see, what is the sine of pi over 2? Well, it's a sine of 90 degrees. Let's remember what the sine is. The sine is here. At pi over 2, it's 1. And then what is the sine of 0? It's 0. And so 1 minus 0 is 1. And it turns out this area, by golly, is exactly 1 square unit. Now, if you didn't remember what the sine of pi over 2 was, you take your trusty calculator and you take pi divided by 2 equals and take the sine of it. And sure enough, it's 1. And of course, 0, the sine of 0, put in 0 and take the sine of that, and you get 0. So if you didn't remember it, you would do that. As a matter of fact, let me suppose sort of a similar problem. I just want to know what is the area under the cosine curve, and I want to start at 0.2, and I want to go, let's see, pi over 2, and let's see what that is in decimal term. Pi over 2 is making up a problem, is 1.57, so I'm going to come out here to 1.4, because pi over 2 is 1.57. I just saw that on my calculator, and I want to know what's this area. Now, this would be quite a challenging problem to do if you didn't have the fundamental theorem of calculus, because, well, what you'd have to do is divide this into lots and lots of little rectangles and calculate, for everyone, calculate the cosine of that point, and then calculate the area, and then add them all up. And a lot of arithmetic. If you didn't have a computer, or at least a calculator, in fact, it would be difficult even with a calculator, because it would just be so much busy work. But it's very easy now. The definite integral from 0.2 to 1.4 of the cosine of x is going to be what? Well, we know that the antiderivative is sine x, so this is going to be the sine of 1.4 minus the sine of 0.2. And now our ancestors had to use trig tables at this point in time. We're going to use the calculator. The ancestors did have trig tables to use, most of them, once they got going. And so 1.4, and I take the sine of that, and that is some number. I'm going to let's see, that's 0.9854. I'm just going to write it down. And then I'm going to subtract, take 0.2, take the sine of that, which is 0.1987, and hit the equal sign, and that should be the answer. 0.7, if I fix this to 4 decimal places, 0.7868. Now, let me tell you something. If you think this is not an impressive thing, you go back and you try to actually calculate the area under the cosine curve from 0.2 to 1.4 and get it to within this degree of accuracy. That would be a very monumental, difficult task without a computer, or even without even using a calculator if you didn't have the fundamental theorem. This was the fundamental theorem of calculus that did this. Now I'm just going to give you a couple more examples to point out to you what this did for our ancestors, so hopefully you'll have a full appreciation of why the fundamental theorem let us move forward as it did historically. Let's suppose that somewhere along the line you came across this function, 2x cosine of x squared. Now, I made up this problem in advance. I knew that if I come up here and if I take the sine of x squared and if I differentiate it using what's called the chain rule, I would get 2x cosine of x squared. This is pretty easy to do. This is something you learn in Calc 1, and it's easy to go from here down to here. So that's in my table now. But now suppose that somebody asks me, what is the area under this curve from, say, 0 to 1? What is the area under this curve? I'm not even going to graph it. You could graph it if you want to take the time to do it. And what is the area? Well, we've got an antiderivative, don't we? The antiderivative of this is sine of x squared. So all I've got to do is put in sine of 1 squared minus sine of 0 squared. And then if I go to my trig table, in my case the calculator, I'll take 1 squared, which is 1. I'll take the sine, and that is 0.8415. And then subtract minus sine of 0 squared, but the sine of 0 is 0, so there's the final answer. So just this quick, I was able to do this problem. Find the area. And it doesn't, you can see it doesn't matter what these limits are. If you've got a calculator or trig tables, it's just as quick to do it. I could have put in 0.3 and 0.9, and it would be just as quick to do it. But the key was the fundamental theorem. And the fact I knew this antiderivative. Now, suppose I took this problem, cosine of x squared, and I said I want to know its integral, just the cosine of x squared from 0 to 1. Guess what? You come back here and go up and look for an antiderivative, and I will bet you could look all day long and you're not going to find one. You search and search and search, and you're not going to find it. You might, but it's unlikely. This is because there's not a simple function who will yield this as a derivative. That's the problem. As a matter of fact, this leads to a whole new function called, I believe I'm right about this, called a Fresnel integral. And and of course they've got tables of them and so on. Now, if you use Mathematica, you would get an answer almost immediately if you use that tool. But Mathematica knows how to evaluate it, and but it's very hard to do with a standard table of integrals. So this is a problem, for example, that we would not have given our students in calculus 30 years ago because there was no easy way for them to find an antiderivative. And of course, we always want to just give them problems that we know they can do. So we figure them out in advance. Like I did this one, I started with something and took its derivative, so I knew there was an antiderivative. Here I just started with a function and I don't know what the antiderivative is. Let me give you another example that you might find interesting. Let's see. I told you that if you take the natural log of x, this is its graph, that will, and take its derivative, you'll get 1 over x, which is a hyperbola, y equals 1 over x. Now suppose I said I want to know the area from 1, and I'll go out to the magic number e. You may recall, you may or may not know this. If you've been through my tier 4 of mathematics, you'll know what e is. And I want to know the area under this curve, 1 over x, from 0 to e. Well, we know that the antiderivative of 1 over x, if this is its derivative, the antiderivative is the natural log of x. So this is the natural log of e minus the natural log of 0. And the natural log of e is 1, and the natural log of 0 is, I'm sorry, I'm going from 1 to e. The natural log of e is 1, and the natural log of 1 is 0. And so the answer is 1. So look what we've got here. This is another way to kind of define an alternative definition of the number e. You take the hyperbola, y equals 1 over x, that is a hyperbola, and you take the area and you go out to the number where this area adds up to 1, and that is a number e. So that's a geometric representation of the number e. It's not the way it's normally defined, but that's what it turns out to be. So you might find that a little bit interesting. Let me think. What else could I do for you here that you may or may not find interesting? I think I had another idea or two, but what were they? Well, you get the idea, I think. Anyway, of this thing. The whole idea is if you can find an antiderivative, you're in business. Now, there's extensive tables of antiderivatives. Well, derivatives, and then of course they're antiderivatives. And these were compiled by our ancestors because they never knew when they'd want to use one. So they'd say, well, all right, let's take the sine of the square root of x squared plus 1. What's its derivative? Now, it's easy to do the derivative. Well, the derivative turns out to be the cosine of the square root of x squared plus 1. You multiply that times, let's see, 1/2 of x squared plus 1 to the minus 1/2. You multiply that times 2x, and that turns out to be, that whole thing is the derivative of that. So if you ran across this somewhere, you'd know the antiderivative. Now, this, by the way, I use something called the chain rule to do this, and it's very easy to learn, and it's very easy to teach students to do that. The problem is going the other direction. If I gave you this right here, and I said, find its antiderivative, well, my goodness, you would have a heck of a time going back, probably, and finding that it was this. You might be able to, but if there was any changes at all, it would be very hard to find. It's there, but what is it? And therein lies the problem our ancestors had. Even though they had extensive tables of antiderivatives, very often they still had a hard time working backwards and finding it. In fact, the bigger the table, the harder maybe it might be to find. So it was really doing integration back in the old days was very challenging. They called that techniques of integration, and that was where you had to find an antiderivative, because without that you couldn't use the fundamental theorem. Techniques of integration are all about using the fundamental theorem. So now the question becomes, if techniques of integration are so difficult, what can we do about it today? What is done about it today with modern technology? And that's what I'm going to be telling you about in the remainder of this video. As I mentioned in the introductory video, the man that is often most associated with this, with calculus, is a man by the name of Isaac Newton. Now Leibniz, Newton was from England and Leibniz was from the continent, from Germany. And they're both associated with calculus, and they both made this discovery independently. But Newton went ahead and applied this wonderful fundamental theorem of calculus, FTC I'll call it, to create modern physics as we know it today, at least as we know it for most of engineering applications. It's called Newtonian physics. And he wrote a book called Principia Mathematica. And this was published in, I want to say 1687. I think it was the publication date on it, the original one. And now, by the way, if you buy this book and read it, you will not see any calculus in it. It's all looks geometry. He did his actual proofs with geometry, but he made his discoveries using calculus. And there were historical reasons why he didn't want to include the calculus as he presented this, and I won't get into that now. That's a whole nother interesting subject. But Newton basically laid the groundwork for modern engineering and technology with what he discovered in Principia Mathematica, and also modern astrology, astronomy, and things like that. Now, the Industrial Revolution that took place in it started really in the 1800s big time. It started before then. It started somewhat in the 1700s, but really in the 1800s and the 1900s, early 1900s, was based on Newton's, this modern technology, and this was based on Newton's great physics theories, and there were other things involved too, but this was probably the core of it. And all of that was based on the fact that Newton and some of his co-workers had discovered this fundamental theorem of calculus. So I wanted to tell you about that. Now, a question we have today is, as we teach calculus, is what's the right way to teach calculus? Historically, in what you normally would call Calc 1, we learn about derivatives. And as I told you in that first video on derivatives, it's pretty easy to make a table of derivatives. Going from f of x to f prime of x is really pretty easy for what you would call the standard functions. Then in Calc 2 is when you start applying integration or integrals. And to do that, you have to use a fundamental theorem, and now you've got to go to the antiderivative. If you take a function g, you've got to go to its antiderivative in order to evaluate the integral. And this is the difficult part. This is the hard part. And this is sometimes called techniques of integration. Really should be called techniques of anti-differentiation, but since you're applying it to integration, it's called techniques of integration. And it's really based on a bunch of what I would call, well, pardon my spelling here, of integration. It's based on really a bunch of ad hoc techniques that are developed. For every rule you have for derivatives, you can kind of have a reverse rule. For example, if you recall the Leibniz rule for taking derivatives. Both Newton and Leibniz knew this rule, but it's called the Leibniz rule. It's for the product of the derivative of the product of two functions. Then this leads to a technique of integration or anti-derivatives called integration by parts. So if you want to go read up on that, this would be an example. Now there's many other examples of how you can use what you learned from differentiation to do integration. But it's not easy. It's pretty difficult. In fact, I would say back many years ago, Calculus 2, techniques of integration, probably, in my experience, caused more students to fail in engineering schools than any other single thing, because these are ad hoc techniques. They're not particularly easy to learn. It's time consuming, it's messy. Now it turns out that to teach calculus today is a completely different ball game than it was back a few decades ago. You don't have to go too far back. The problem, as I said earlier, is you're either given a function and you've got to find its derivative. That's not too hard. But the harder problem is you're given a function and you've got to find its antiderivative, and that's hard. This is easy. I'm talking relative now. I mean, you can certainly get into a mess here, and this can be time consuming, but this can be really, truly challenging and difficult. There is a wonderful tool now that came out. In 1988, a marvelous tool was developed, and it's called, ironically enough, Mathematica. And I'm sure that, well, I'm not sure, but I'm rather guessing that the developer of this tool, Stephen Wolfram, was probably referring this back to the great Newton's book, Principia Mathematica. And this is just an example of one of the books I've had that's been around quite a while on Mathematica. And this is all about using Mathematica to do all kinds of math problems. But in particular, if you plug in a function into Mathematica, it will immediately give you the derivative. And what is even more impressive to me, if you plug a function in, it will give you the antiderivative. I might also tell you that there are many situations where you have a function and it doesn't come from an obvious function. For example, and there's many examples of this, I'll just give you one. If you take the antiderivative of the sine of x, for example, I'll say sine of t dt, 0 to x, and you take its antiderivative, you're going to get the cosine of x, as we talked about before. I think I did that right. But what if you want to take the antiderivative of the sine of t squared dt from, say, 0 to x? What would you get? And now the answer is not some ordinary function. This turns out to be, they give this a name, they call it sine of x, and this is called a Fresnel integral because it's not one of the ordinary basic functions. But it turns out this is something you need to use in optics, for example. And so this is actually a way to define new function, is to say, okay, I've got a function, its antiderivative is a new function, I give it a name. And there's lots of examples of that in mathematics where they've done it. Well, Mathematica handles all of that for you wonderfully. And like I said, it came out in 1988. It's a program. It costs some money. There's a student version of it. But remarkably enough, in the year 2009, Wolfram released a version of it. It's called Wolfram. Steve Wolfram was the inventor of Mathematica, and this is called Wolfram Alpha. And this is a free version on the web or the internet. And that is just an amazing thing. And so that's what we use today in our Tier 5 when we teach calculus. We do not spend very much time teaching students how to evaluate derivatives and integrals, particularly integrals, because it's so difficult to do and time consuming. And as a matter of fact, nobody today, in my opinion, that's applied mathematician, if they had a function and they needed its antiderivative, they wouldn't sit around and spend a lot of time trying to apply the techniques to find it. They would just take a tool like Mathematica and do it. Mathematica does for calculus and differential equations and other things what the calculator has done for arithmetic. As you may recall, in our foundations course, we teach the student, for those of you if you're not familiar with it, we teach a student all of the algebra and geometry and trigonometry that they need to know to do most practical math problems in about 3 months of their time. And the key to that, one of the keys is that we use this power tool of the calculator. This is a $10 calculator that lets you do all sorts of things. And I might add, when we start teaching calculus, we use the calculator to have the students actually calculate derivatives of some of the more common functions. Now this doesn't do what Mathematica does. It doesn't give you the global definition, but you can calculate the specific derivative at any particular point with a calculator very easily. We didn't do that many years ago before calculators came along because it was just too cumbersome. But it's a great learning tool. It's a great way to learn what it is. Let me just give you a very quick example of that. I want to know what is the derivative of the sine evaluated of the sine of x, but I want to know what it is at, let's say, 45 degrees. That's pi over 4, okay? What is the sine? What is the derivative? Well, to do that with a calculator, first of all, I have to change it to radian measure. So I have to do that. I'm in radian measure now. And what I do is I take pi divided by 4, and I just happen to know from experience that that's 45 degrees, so pi over 4. And I'm going to store that in a register here. And I'm going to add to that a very small dx. So I'm going to add to that 0.0001. I have 0.3001. I'm going to add to that. And I'm going to take the sine of that. And then I'm going to subtract, and then I'm going to recall the pi over 4 and take the sine of that. But hit equal. I'm going to divide that by 0.0001, and that equals, and the answer is 0.707. Now, I'm going to take pi over 4 and hit equal, and I'm going to take the cosine of that, and sure enough, I get the same answer. So I've proven now that the derivative of the sine of pi over 4 is the cosine of pi over 4. And it's just coincidental they're both 0.707. I should have used a different one here to make the point more clearly. But you can do that on your own if you want to. You can take the derivative of the sine of pi over 7 and do what I just did, and then you'll get a number. And then you take the cosine of pi over 7, and you get the same number. And so that's just a way of applying that. In any event, to summarize this, our ancestors, first of all, even starting with the Greeks, were concerned about rates of change, and that leads to the concept, if this is f of x, to the derivative, f prime of x, some kind of a function. And then they were also interested in areas or integrals. Our ancestors, or Archimedes, was interested in this. And so you wanted to find the area under a curve. And that led to the concept then in modern times, in the 1600s, of antiderivatives. And the fundamental theorem of calculus connected these two together. It lets you now have a way to calculate integrals by using antiderivatives. And in modern times, to make this easy to do, you have the modern tool. Newton provided the theoretical tool for this. Newton proved, as and his colleagues, that the antiderivative was the key to doing integrals, and Stephen Wolfram then exploited that and created the tool, the modern tool, to actually do it. So you can actually plug in the f prime of x into Mathematica, and it will give you the antiderivative. And so that's really what I wanted to tell you about calculus. And then I might just add that the integrals then, of course, applies, as I said, to all sorts of things in engineering and science. But those two things together were really the Rosetta Stone, if you want to, or it was the key, the open sesame to modern technology. And we all, if we are enjoying our modern civilization, we all have Newton and Leibniz and all of their fellow mathematicians to thank for these inventions and then the subsequent development of technology to all the people that followed. So this is Dr. Dell signing off. I hope you've enjoyed it, and I will see you on another video. Bye-bye.